Hi everybody, and welcome to this presentation of the paper Quantifying Measurement Quality and Load Distribution in Tor at ACSAC 2020. In this paper, we will look at Tor's load balancing mechanism and analyze why it has severe deficiencies regarding quality and security. We will start with a quick introduction into the research objective. With Tor, traffic is forwarded by relays that can be used for privacy-preserving paths called circuits. This way, an attacker can only observe the communication from the client of the first relay and from the exit node to the web service, guaranteeing anonymous communication over the internet. However, before a client can build a circuit, knowledge about existing relays is necessary. In Tor, this topology information is distributed in the so-called consensus document. In order to appear in a consensus, a relay has to register itself to the directory authorities. These authorities will then include access information of this relay, like the IP address, in the consensus. Additionally, a subset of the directory authorities also act as bandwidth authorities and measure the available bandwidth of the relays. This is used for load balancing. Clients will select relays for a circuit proportionally to these measurement results. In this paper, we want to analyze the quality of these measurements, the resulting load distribution, and the security consideration following from them. And indeed, these measurements are crucial to the security of Tor. We already know that clients use these measurement results as selection probability. However, relays are able to perform de-anonymization attacks if they attract too much traffic. If a relay is the first hop in a circuit, it knows about the Tor user. If a relay is the second hop in a circuit, it may know about the content of the stream. If both the entry and the exit relay is controlled by an attacker, he can perform a powerful traffic correlation attack and know about both the client and the content of the stream. Because of this, traffic in Tor should be distributed to as many entities as possible, and relays should not be able to influence the amount of traffic they attract. Hence, secure and accurate measurements are crucial for the security of Tor. As of 2020, the bandwidth authorities collect their measurements by building a two-hop circuit with a relay under measurement and another faster relay. The average bandwidth provided by the circuit is then used as measurement result. Afterwards, multiple measurement results and the self-advertised bandwidth of this relay are aggregated to the consensus bandwidth that is then used for load balancing. Based on this load balancing process, we want to analyze three things. First of all, we want to evaluate the quality of the measurement process. We will see that there are severe shortcomings and that we effectively cannot verify the bandwidth of fast relays. Secondly, we want to analyze the resulting load distribution in Tor and how this simplifies the de-anonymization attacks introduced earlier. And lastly, we want to analyze how much bandwidth is attracted by high bandwidth relays that we cannot verify by measurements. To evaluate the quality of measurements, we want to analyze whether the measurement results are aligned to a ground truth bandwidth. To do this, we used Tor's measurement approach and collected more than 1 million measurements of real-world Tor relays over 2 months. For our analysis, we want to look into the alignment of these measurement results to the actual bandwidth of the relay. However, unfortunately for us, such an analysis is impossible as the actual bandwidth is unknown. While it would be possible to use a simulator to collect this information, this would also exclude the important effects of real-world traffic handling on the measurement results. As such, it is more desirable to analyze the measurements using a different method. Luckily for us, we already know that the actual bandwidth of relays changes only infrequently. But this means that we can use this information to follow a different approach. If the ground truth changes only infrequently, we can also analyze the alignment of multiple measurements to each other. More precisely, we use the correlation of the relative position of the measurement result in the list of all measurement results over time. If the measurements are reliable, this relative position should be stable and, as such, correlate strongly over time. However, our evaluation shows that this is not the case. Instead, measurements are stable only for low bandwidth relays. While there still is a significant correlation for medium bandwidth relays, multiple measurements are uncorrelated for high bandwidth relays. Even more concerning, for these high bandwidth relays, the measurements are negatively correlated both with the self-advertised bandwidth of this relay as well as the consensus bandwidth to this relay. Instead, the consensus bandwidth correlates highly with the self-advertised bandwidth. This means that the traffic attracted by high bandwidth relays is influenced more by the untrusted self-advertised bandwidth rather than measurements. This is concerning as it allows high bandwidth relays to attract more traffic by lying about their bandwidth. In this next section, we want to analyze the distribution of traffic to different relays. More precisely, we want to evaluate how reasonably an attacker can surveil popular relays or attract traffic to his own relays to perform a large-scale de-anonymization of Tor users with the traffic correlation attacks introduced earlier. To give an answer to this question, we analyzed the load distribution in Tor. We did so by building more than 12 million real-world circuits and analyzing how often certain relays were selected for these circuits. Again, our results are concerning for the security of Tor. In practice, only few nodes handle the majority of traffic. For example, a single relay forwards almost 2% of Tor's exit traffic. Furthermore, only 10% of all relays are responsible for handling the majority of Tor's traffic at both the entry and exit position. Overall, focusing on popular relays greatly simplifies the amount of relays needed to de-anonymize traffic in Tor, compared to a fictive Tor network where all entities are selected with the same probability. Most de-anonymization attacks get around 80% easier. Most concerning, surveilling the majority of exit traffic currently only requires around 125 relays. As such, this attack gets more than 95% easier if the attacker focuses on popular relays. Overall, the load balancing process leads to a heavy centralization of traffic to only a few entities in Tor. In this last section, we want to merge the results of the first two analyses. From the first analysis, we got to know that we cannot verify the bandwidth of high bandwidth relays. In the second analysis, we figured that only a small fraction of high bandwidth relays are responsible for handling the majority of traffic. In this analysis, we want to quantify exactly how much of Tor's traffic is assigned to entities that we cannot verify by measurements. Based on a very generous interpretation of the results from the first study, we assume that we can accurately determine the bandwidth of relays that offer less than 300 kilobytes per second. Furthermore, we assume that we can accurately use measurements to detect relays lying about their bandwidth if these relays provide between 300 and 500 kilobytes per second. However, we are unable to verify the bandwidth of faster relays. Note again that this categorization is very generous, as it assumes that any correlation between multiple measurement results is sufficient to accurately determine the accuracy of third measurements. However, even when using these assumptions, the results are concerning. Under this assumption, almost 90% of entry and 40% of the exit traffic is currently attracted by relays whose bandwidth cannot be verified by measurements. Looking at the whole picture, more than 90% of Tor's traffic is assigned to circuits in which either the entry or the exit relay cannot be verified by measurements. Overall, this undermines the central point of the measurement and load balancing process. As of right now, the vast majority of traffic is attracted by relays whose bandwidth cannot be verified by measurements. Instead, the traffic attracted by these entities relies primarily on the untrusted self-advertised values. To summarize, in our paper, we analyzed the quality of bandwidth measurements in Tor. We found several severe shortcomings, especially for high bandwidth relays. A following analysis of the load distribution in Tor showed that only few entities are responsible for handling the majority of traffic in Tor. This reduces the amount of relays necessary to perform various large-scale de-anonymization attacks by more than 80% simply by focusing on popular relays. Lastly, we showed that currently the majority of Tor's traffic is assigned to relays whose bandwidth we cannot verify, undermining the central goal of the Tor Load Balancing Mechanism. Based on our results, we argue that more attention should be devoted to the quality of bandwidth measurement and the security of load distribution in Tor. Currently, much of the research into Tor's load balancing mechanism focuses on improving the performance of circuits. However, as we just saw, increasing the utilization of low bandwidth relay strengthens decentralization in Tor and complicates large-scale de-anonymization attacks. Furthermore, we think it is worth discussing about research approaches into the Tor load balancing process. Up to now, there's little consensus on how to define metrics and interpret results or trade-offs like the trade-off between load decentralization and circuit performance. This makes it more difficult for Tor developers and researchers alike to get a complete picture of Tor's load balancing process and to actually implement suggestions into Tor. Finally, we want to thank you all for your attention. You can read the full open access paper online by scanning the QR code shown on this slide. We look forward to hear comments on our work and to discuss these results at ACSAC 2020. Take care and stay safe.